Hello and welcome, everyone. My name is Rick Spijkers. I'm from the University of Twente, and the topic of today is the physics of absorption and evaporation of liquid nitrogen in a porous medium. So, in the field of medicine, at the moment, there is a shift from the one size fits all, one pill solution to a tailor-made solution for patients. Think of gene therapies, for example, and for this, you need to transport biological samples from the hospital to specialized laboratories, and the medicine has to be transported back to the hospital to be administered to the patients. This is done using so-called dryshippers, in which the samples are transported at a temperature of minus 196 degrees centigrade to preserve the samples correctly. So you might think in my lab I also have a Dura, and this is also at the same cold temperature. Why not use this one? That is because a Dura is not allowed to be transported in an airplane, because if liquid nitrogen spills out, it expands enormously and you cannot simply open a window in an airplane and let oxygen back in. So in a dry shipper as a solution, the liquid nitrogen is absorbed in a porous material. So afterwards you can hold this dry shipper upside down and no liquid nitrogen comes out. However, the vapor that comes off this material when the liquid nitrogen evaporates still cools your samples. So, and here you see an example of a porous material, which is a brick-like material with a lot of open spaces in it and channels for liquid to flow through. So a typical transport company would start by filling a dry shipper. So what they do is they fill it first, but the dry shipper needs time to absorb the liquid nitrogen. And they also have to repeatedly fill this dry shipper so that it can absorb the maximum amount of liquid nitrogen. And afterwards it needs to be filled and left to absorb the last amount, just to guarantee the proper cold storage time. So after filling, the dry shipper is transported to the customer, for example, a hospital, where they put in their samples, and then it's picked up again and brought to the airport, where it is flown to the final destination. This could be a non-direct flight, so it could take several steps, and then it has to go through customs, and then is picked up and brought to the final destination, where the samples might still be stored in this dry shipper. So as you can see, there are a lot of steps involved in this process. And if, for example, at customs something goes wrong, you don't want your precious medicine to be destroyed because the dry shipper heats up. So there are two pain points. So the first one I just told you, which is the cold storage time. And the second is the filling time, which could be up to 16 hours. My research question is, what is the interplay between porous materials and cryogenic liquid properties during imbibition? So I want to understand how liquid nitrogen is absorbed in a dry shipper. And as a model problem, I will study the absorption of a liquid in a porous material. This because if we understand how it is absorbed in the porous material, we can translate this to the larger scale. Similarly, a capillary, which is a small tube, is a model problem for the porous material, because as you can imagine, the porous material consists of pores, which are interconnected by channels through which liquid flows. So on a microscopic level, they are the same. You have liquid flowing through these small channels, and similar forces are involved. So this is a good model problem. The advantage of a capillary is that you have much more control over the geometry and, for example, the radius of the capillary, and it is of constant cross-section, and you can see where the liquid is with, for example, a high-speed camera. So if we understand it now at this microscopic scale, then this can be translated to the scale of the porous material. And that's why capillary is a good model problem for the microscale.